Hello everyone, I am Abhishek Mandal and this is my presentation on effect of composition and heat treatment on the mechanical properties of FeMnAl steels. So what are FeMnAlC steels? FeMnAlC steels are generally known as Poorman steels, were developed to replace conventional nickel chromium steels due to the attractive properties of strength and ductility. These steels nowadays are generally used to make automotive and cryogenic components in industries. So in this research, 4 different kinds of rolled steels of 5 mm thickness were studied with different amount of aluminum, manganese and carbon, which is shown in the table below. The densities and hardness values of these 4 different kinds of steels are also shown. In order to perform the experiments, all the 4 steels were cut according to ASTM EHM standards for doing tensile test. 3 specimens were made for each test conditions. Also, a 25 mm by 25 mm section was cut in order to perform hardness tests at different aging durations. In as received conditions, all the 4 alloys shows austenitic structure with visible twins with an average grain size of 50 to 200 micrometers as shown in this slide. Here on the left, when the specimen were subjected to aging at 550 to 700 degrees Celsius after solubilizing at 1030 degrees for half an hour shown by blue line, and after solubilizing at 1050 for 1 hour shown by red line, it can be seen that the alloy B22 and B23 show an increase in their hardness while B37 and B44 remains almost constant. This behavior is due to the higher quantity of aluminium in B22 and B23. On the right, the stress strain curve of B23 and B37 is shown before and after aging at 550 degrees Celsius for 8 hours. It is seen that the B23 show a very brittle behavior after 8 hours of aging and breaks in the elastic region. Again, this is due to the higher quantity of aluminium in B23. The microstructural analysis of all the alloys after 8 hours of aging show that B41 and B37 still have the typical austenitic structure as before the heat treatment, while B23 develops different phases and B22 still has the austenitic structure with more rounded grains. An XRD analysis of B23 before and after aging show that after the heat treatment, B23 develops intermetallic phases, which explains the change in its microstructure and its brittle behavior during tensile test. Finally, the same analysis of the fracture surfaces of B23 and B37 show that B37 shows a ductile fracture before and after heat treatment, while B23 shows a brittle fracture characterized by transgranular fracture with secondary microcracks. Hence, it can be concluded that the composition of the studied steel affect their behavior, especially when they work at a temperature above the range of 500 to 700 degrees Celsius. Alloys that shows that they are characterized by austenitic structure in as received state, but solution treatment aging have different effects on their microstructure and mechanical properties. Also, the alloy characterized by high content of aluminum and manganese after heat treatment produce the formation of brittle intermetallic phases that determine the brittle behavior of the alloy. Hence, it can be said that optimizing the chemical composition is of paramount importance to guarantee a high ductility and fracture toughness when the component is put into service at high temperature.